We have a set of data that will yield a least squares regression line of 55.402 minus 1.531x. X here is the Tug score, Y is the Berg score. It can be shown that if you find the sample correlation for this data set that you'll get R equal to negative 0.885. If that had not been given to us, you could use the tools we learned in Chapter 3 to find that. What we want to find out is if there's some correlation between these variables in the population. So the R we're given is the sample correlation, and we want to know if we would still have a correlation if we were to look at the whole population from which this data was drawn. And then we want to know how would that test statistic that we get relate to what we got when we looked at a population slope, finding out what the population slope was. So in testing for a population correlation, we're going to test if it's equal to 0, and we use the Greek letter rho to stand for population correlation. So our null is if rho is equal to 0. We just want to know if there's some correlation. We're not asked if there's a negative or positive correlation. So when we're doing just some correlation, we want to test if rho is not equal to 0 as our alternative hypothesis. The test statistic that we use for testing for correlation takes our sample correlation R times the square root of n minus 2 over the square root of 1 minus our R squared. So plugging in all the quantities, we'll get negative 0.885 times the square root of 16 minus 2 over square root of 1 minus negative 0.885 squared. And what we arrive at is negative 7.112. The degrees of freedom is n minus 2, and so we're using 14. So we want to go look for 7.112 in our t-table in row 14 to try to bound our p-value. Keeping in mind we're going to be doing a two-tailed test and not equal to, so when we get our bounds we'll need to multiply that by 2. So looking in row 14 for our quantity, what you will find is that it is off the chart in the positive end. So here's row 14. As we go through and look at the numbers, what we'll find is that the largest value that we end up with is this 4.14, and our number is larger than that. The tail area for 4.14 is 0.0005, and so our number, the 7.112, is even farther out in the tail, meaning it has a tail area that's even smaller than 0.0005. So we'd get a p-value less than this quantity, but we need to multiply by 2 since we're doing a two-tailed test. So we find that our p-value is less than 2 times 0.0005 as our bound that we got from the table. So we get a p-value less than 0.001. With a small p-value, we will reject the null and say that we have significant evidence that there is some, we can say here, a linear relationship. Since there is a correlation, there would be a linear relationship between Tug and Berg score in the population. And we're also asked the question then, how would this test statistic we got compare to if we were testing for a population slope? It turns out that even though the formulas look very different for this test and testing for the population slope, that they are equivalent. So if you would look back at the podcast for testing for a population slope, you'll find that we got something very similar to negative 7.112, and they're off slightly just due to rounding of quantities along the way. So if you're asked the question if you have a linear relationship in the population, there's actually two ways to arrive at that answer. You could do this test for the correlation, or you could do the test for the population slope, because they're really answering the same question as to whether you have a linear relationship. Which one you choose to do may just depend on what quantities you're given to start with. You can see that this formula requires the correlation and sample size, whereas the formula when finding the test statistic for the population slope required the sample slope and the standard error of that quantity.